Hello PChem peeps, and welcome to another week of recitation videos. So this week we're going to be talking about Raoult's law and the ideal gases, relating Raoult's law to Thermo, and going over some of the problem set 1 problems, because there seem to be some pretty common problems that I saw come up while grading, and I wanted to clarify stuff and help you figure out how to go about solving problems a little bit more efficiently. So let's look at Raoult's law and the ideal gases. So these come mostly from the book. We haven't talked about them a whole lot in class. So I'm going to go over them in a little bit more detail and how you can go about applying them. So first, let's start with mixing gases. So we have A moles of A, B moles of B, and that goes to C moles of C and D moles of D. So what we can do is actually solve for the mole fraction of this, which is delimited by chi sub A. So this means that we're going to find the percentage of moles of A from the total moles of the system. So when we do this, we do our N, or moles of A, divided by the sum of all of the moles in our system, which is where we get the denominator. And that gives us our chi sub A. Then we can actually look at P total, and P total is going to be equal to the pressure applied by A, B, C, and D, which makes a lot of sense. You're going to receive total pressure based on everything you see in a system. What we can do is solve for each of those partial pressures by multiplying the total pressure by chi sub A. So this comes from the ideal gases. This says that whatever percentage of moles each different molecule is going to be your partial pressure applied by that molecule from your total, which is where we get that equation, as I said. So let's remember some equations that we've used before. So remember that delta G over delta P with respect to N and T is equal to V. So G is going to be equal to G naught plus nRT ln of PF over PO, which remember we can also substitute V in there and solve for the equation that way, which we did on our previous homework. And again, remember that V is equal to nRT over P. So using that, we can say that G sub A of the mixture is equal to G naught sub A plus nRT ln of chi A. And again, we can do that for B as well. And then we can expand this to say that G sub total is equal to G sub A, B, C, and D of the mixture, and they're a standard equation. Expanding this out a little bit, we can get G sub total is equal to G naught of the products minus G naught of the reactants plus nRT ln of chi sub C raised to the C, chi sub D raised to the D divided by chi sub A raised to the A, chi sub B raised to the B. And all of that part within the ln function is equal to K. So if we sub that in, we just get this really nice equation that is delta G total is equal to delta G products minus reactants plus nRT ln of K. So now we're going to look at Raoult's law and see what that really says for us and what that helps us do. So overall, Raoult's law says that the mole fraction in solution is equal to the mole fraction in gas. So chi sub A solution is equal to chi sub A of gas. And this allows us to say that K solution is equal to K of gas. And we can substitute in the K solution in that way, and then we're going to actually try to apply this. So remember that standard state of solution, T is equal to 298 Kelvin, pressure is equal to 1 bar, pH is equal to 7, and concentration is 1 molar. So thinking back to your previous classes, you've probably seen this equation before. K is equal to the concentration of C raised to the C, D concentration raised to the D divided by A concentration raised to the A, and B concentration raised to the B. Now let's go ahead and say that K solution is equal to 1. So all of that above is equal to 1. What is going to happen? So our delta G is going to equal delta G naught because ln of 1 is going to be 0, so that whole part of the equation falls out. So our free energy of standard state is defined as G naught. Another thing we can look at is delta G at 0. So when we do this, we can rearrange the equation to say that delta G naught is equal to nRT ln of K. So delta G naught is measured at equilibrium even though it is defined at standard state. It's It's an interesting way of going about it, but this is how we have to go about solving for the two different pieces, delta G and delta G naught. Okay, so let's look at problem set 1, 6.2. There were a lot of problems that I saw with this, so I want to go over some of the main things that I saw that I was concerned about and things that you can do in order to solve this question most efficiently. So 1 mole of an ideal monoatomic gas is initially at 300 K and 1010 joules per liter pressure inside a cylinder with a frictionless piston. The gas expands until the pressure is 101 joules per liter. Calculate delta U, the change in energy, Q, the heat transferred to the system, and W, the work done by the system, when the expansion is isothermal and reversible. So the first thing that I do whenever I come across a word problem is to list out everything that I know based on the question and everything that I don't know and that I'm trying to figure out. So first we have that our number of moles is equal to 1 because they told us at the very beginning. Our temperature is equal to 300 Kelvin. Our initial pressure is equal to 1010 joules per liter. Our final pressure is 101 joules per liter. And the R value that we're going to be using based on the units that we have in this equation are going to be 8.314 liters times kilopascals, Kelvin times moles. So now we're going to be looking at what we need to solve for. So we need to look for delta U, we need to look for Q, and we need to look for W. So the first thing is to look back at the question. There's something that they told us that will help us solve a lot of stuff very quickly, and that is the fact that we have an isothermal system. So when there's an isothermal system, there's no change in temperature. So delta U is going to be equal to 0. So that means that we can do some equation rearrangement and show that Q is equal to negative W. We also know that Q is equal to T delta S, and that delta S is equal to NR ln of VF over VI. And then we can look back at our ideal gas law and see that VI is equal to nRT over PI. So now we can solve for our two different V values. So we can solve for VF and VI. And that can help us solve for delta S, which can give you Q, which can give you W. So when we do that, we get our two different V values, which is 23.98 liters and 239.8 liters. So when we solve for our delta S value, we get 19.1 liters times kilopascals per Kelvin, and then we can plug that into our T delta S equation to solve for Q, and we get 5,743 joules, and then for W, it's the negative of that, so we get negative 5,743. So an important thing to remember is that we added heat to this system, so that means that Q is going to be positive, and then it did work on the system. So that means that the work is going to be negative, and that's where those two values come from. So looking at 8.1, there were some other problems that I saw come up, and hopefully this clarifies a little bit. So a system starts with a multiplicity of 2,000. 2 kilojoules of heat are transferred into the system reversibly at 298 K. What is the multiplicity now? And assume that Kb is equal to 1 joules per Kelvin. So again, we're going to list out everything that we know. So W1 is going to be equal to 2,000. We had 2 kilojoules of heat that are transferred to the system, so Q is equal to 2,000 joules. T equals to 298 Kelvin. Kb is going to be 1 joule per Kelvin. This is not always it, but it's telling us to assume that. Our moles are going to be 1N. And R that we're going to be using is 8.3145 joules per kmol. Now we're going to solve for W2. So let's look at some equations that we have that will help us solve for this. So remember, Q is equal to delta S times T, and then S is equal to Kb ln of W. So now what we can do is solve for delta S, we can solve for S2, and we can solve for S1. So we can go about doing that first by solving for delta S. So we're going to use the Q equals T delta S, and we can rearrange that so that it's delta S is equal to Q over T, and then we get a delta S value of 6.71 joules per Kelvin. Now we have our initial W value, which can give you your initial S value. So when you solve for that, you get 7.6 joules per Kelvin, and now you can use the intrinsic value of delta S, which is S2 minus S1, which rearranges so that you get delta S plus S1, and you get your S2 value of 14.3, which you can then solve to get your W2 value of 1.64 times 10 to the 6th. Overall, for the exam, I've been getting a lot of questions about how you should go about doing stuff. And really what you should do is write down all knowns and unknowns like I did in the before questions. It really helps solidify things and helps you figure out what you need to do and what you should be doing. Then you need to determine your system conditions. Like we did in the 6.2 question, it's an isothermal system, which means that delta U is equal to 0. So you really need to know what those system conditions helps you figure out. And then don't make assumptions that are not called out in the question. I saw a lot in the homework in 6.2 that people assumed that the final pressure was equal to the external pressure, and that is not the case. So make sure that you don't make those kind of assumptions because that will lead to the wrong answer. And just a reminder that exam 1 is during normal lecture time on September 12th. Good luck, everyone.